second.
So yesterday I showed you Green's theorem, and it was really cool because we were able to evaluate some line integrals that looked hideous, but we were able to do it quite easily, right? Using Green's theorem, which allowed you to turn them into a double integral in a much nicer form. So today we want to connect Green's theorem
It's okay, but you need some.
and
Curl.
and div.
Yeah, you will. Okay. But don't start later.
So let me remind you of a few things. So first, Green's theorem.
Oh, I'm gonna miss the next semester.
Which said that,
Hopefully in the same physics.
well, with sufficiently nice conditions on things, that if you take the line integral
Choose integral.
of p dx plus q dy, so remember here, p and q are functions of x and y. P is a function of xy, q is a function of xy. They should have continuous partial derivatives on some region which contains this curve in its interior. So this curve is supposed to be a closed curve. Remember, closed meant that the terminal point and the starting point were the same. So maybe it starts and ends right there. Doesn't matter. It makes a loop. So C is this outside region, and then the inside we call D. And so P and Q should be continuous. Should have continuous partial derivatives on some open region containing D. Right? C should be a nice, simple, smooth curve. And Green's theorem says that computing this line integral is the same thing as computing the double integral over the region D of the partial derivative of Q minus the partial derivative of Y. So this was quite nice because, for instance, your Q might have some really nasty Y component that's separated by, say, a plus from the X component, and then when you take the derivative, the Y component vanishes with respect to X. And so you can get rid of some nastiness, and the same thing for PYs. That's what we saw yesterday. Okay. And what about curl and div? Let's remind you what those were. So the curl is something you did to a vector field, right? And it gave you a new vector field. And the div was, again, something you do to a vector field, but it doesn't give you a vector field out. And it ended up giving you a scalar function. Okay, and let's see. So you might remember that they both use the gradient. And then it's just a matter of remembering what goes in between the gradient. Yeah, and in which order?
Curls the cross.
Curls the cross.
Dot.
Gives the dot. Isn't it so stupid, but it works, right? Curl is a C, C is the cross, D is a div is a D. Has a dot. I love when mnemonics are so natural. What's that?
I think I was absent for that.
Oh, were you not here for? Oh, yeah.
That's pretty clever.
Yeah, C, cross, D. I'm pretty proud of that, actually. They don't write that in the textbooks, do they?
No, they don't. I think you should write your own textbook of all the mnemonics that you've thought of.
Don't conform.
Don't conform?
Don't conform.
Okay, so mnemonics are good until I write a textbook using them. Is that what you're saying?
Yes.
Okay.
Once you write a textbook, you become a slave to the system. Don't do it.
A slave to the system.
Publish your notes online, open source instead. Much better than I
Rage against the machine, baby.
Exactly.
I think you should publish your own music album.
Music album?
Yeah. So
All right, do you guys want to hear my latest song?
Yes, please.
Okay, I wrote this for my 4-year-old who's learning his multiplication tables. It goes like this. 9, 18, 27, 36, 45, 54, 63, 72, 81, 90, no more. Yeah.
You remember
That's
that?
right where the guitar solo would be right after.
When I was young, I used to have a song. I remember it. When I was a kid, I used to have a song. I remember it.
Yeah, I can do
It
it.
doesn't rhyme or anything.
Okay, so, good. So these are the ingredients.
Good, back to class.
Yeah, let's see. Do we need anything else? No. Oh, that's fun. Okay. So, let's put this all together as much as we can. So let's start with a vector field. And we know that we can write it as, say, p of x, y. This will be just a two-dimensional one. Okay, so the component functions of the vector field are p and q. And we know that if you integrate over some contour c, that this is the same thing as integrating p dx plus q dy. Okay. Now, Green's theorem was, of course, for the situation where you're looking at a two-dimensional vector field. And, of course, here we go, two-dimensional vector field, right? It's got the two components. Curl has to do with the cross product. But the cross product is only for what? Three-dimensional stuff. So, this is nonsense, right? You can't take the gradient cross product with a vector field that only has two components to it. Kaiwei.
Can you just say the z part is 0? So
That's a brilliant idea. Okay, let's try that. Let's see if Kaiwei's right. Let's see what happens if we do what Kaiwei's. So we're going to define. We're going to define a new f, and it's going to be p of xy, q of xy, 0. Okay, so this is a new vector field. Good. And we can now define, or we can now write down the curl. Okay, so if we do that, remember there's this way of computing it. You take the determinant of a 3 by 3 matrix, where on the top row, you just put the unit vectors, I, j, k. In the middle row, you put the first thing, and then in the bottom row, you put the components of the second thing. Okay, now this is the partial derivatives. So normally I write partial, del mod del x, right? I want to be lazy. I'm just going to write del x. This means take the partial derivative with respect to x. It's a little shorter, yeah? I'll write here del y and here del z. And then on the bottom I need to write f, which will be p, q, and 0. Okay, and these bars, remember, are meaning take the determinant. And the way we take the determinant of this 3 by 3 matrix, well, we could expand on a row or a column, or we could just use that crosshatch method. And I kind of like the crosshatch method, so let's do that. So if you go this way, you get a 0, so there's nothing for that I. And if you want to do the I the other way, you go this way and here. So you have to take the partial derivative of q with respect to z. But q is a function of x and y, so what happens when you take the partial with respect to z? It's 0. So there's actually no I component at all. Cool. Okay, what about j? So j, you go this way, you do the partial with respect to z of p. P is also still a function of x and y, so that's dead. So let's go the other way. Oh, 0. Huh, so there's no j. Okay. What about k? Okay, we'll go this way. K, you get partial with respect to x of q. Okay, so it's just qx. Right? Partial with respect to x of q is qx. Then you have to go backwards. You do minus the partial with respect to y of p. So minus py. Okay, so the curl of this modified vector field is qx minus py. Well, that should look familiar. Back at Green's theorem. Green's theorem says if you integrate the vector field, you get the double integral of, oh, look at that, qx minus py, the same thing. So, this means that the integral of f can be rewritten as the double integral over d of the curl of f. And now there's a little bit of ambiguity here. When I write the curl of f, it can't be the same f. It has to be this f where we've attached a 0 on the end. All right? So that's a notational abuse we've made. Oh, wait a second. I left something out. Something is horribly wrong here. What is horrible? Who can say what I left out? Well, when I computed this determinant, how did I get that qx? I went along the k, and then I got the partial with respect to x of q. So I wrote down qx. Did I leave something out?
Sure. Okay.
The k. Same thing with the py, right? It's supposed to be multiplying all these things together. So I left out the k. So this is really times k. So if I want to, if I just want to have qx minus py, here's a really slick trick. Take this and take the dot product with k. Right? What's the dot product going to be if you dot product with k? If you do the dot product with k, it's qx minus py, k, dot product, k. Well, you take the coefficients in front of k, which is this and 1, you multiply them, and then there's no other vectors to add up, so it's just this vector here, right? Or this coefficient, qx minus py. It's just like when you do, if you had 2k dot product 4k, it would just be 8. The k's go away. Okay, so to make this correct, we need to take the dot product with k.
So quick question, what happened to the I and j terms again when we were doing the cross product?
So for the I, for instance, if you go this way, you multiply by 0. So nothing there. If you go the other way, you do I times the partial with respect to z of q. But q is a function of just x and y, so the partial with respect to z is 0.
Okay.
And the same thing happens with j. You either multiply by a 0 or you take the partial of p with respect to z. So, why is this interesting? From a physical point of view, what makes this interesting is the curl has a physical interpretation. Right? So you remember if you had some constant flow, right, through a pipe or something, we figured out what the curl was. The curl was if you picked out a point, it was the axis at which, right, things were rotating about, right? How things were curling about that point, right? What did the rotation of the fluid around that point look like? So that's what you're saying. This is giving us an interpretation of the line integral in terms of that rotation. Now, when we write down another one for divergence, of course, well, we had another physical interpretation for that. Namely, the divergence was, right, the rate. It was like what the net rate per unit volume that things were flowing away from that point. And so you look at the stuff coming in, the stuff coming out, this was the net rate. It's how much was diverging from that point. Okay. So we can also, we're going to be able to write down something similar. Okay. So to do the something similar with divergence, I need to tell you about something that we did on the homework, and we looked at something called the tangent vector, right, to a vector function. So really need this. So let's talk about tangent and normal vectors. So I should mention that if you take this course from another instructor, watch one of these courses online, say from MIT or Berkeley, whatever, I think they probably spend a lot more time focusing on tangent and normal vectors. All right. It's not something that I thought fit well into this course, so I didn't really focus on them so much. But if you are interested in this more, and they are incredibly important, you can look at any of those courses online and you'll see a lot of discussion about these. Okay, so let's start with some vector function, r of t. And we'll give its components as x and y. I think I just want 2 for now. Yeah. Okay, and so we'll say t here is going between a and b. So this gives you a curve, c. So let's say this gives a smooth curve c. What would be a reasonable definition of a tangent vector? Well, let's see. Let's go back to calculus, because that's where everything comes from. How did you write down the tangent line to a curve? You needed to know the derivative, right? The derivative gave you the slope of that tangent line. And of course, you had a point, so you could use the point slope form. Okay, so we're going to define a new vector, which we'll call t of t, confusingly. And all it's going to be is that every point, it's going to write down the derivative of the component functions. So this is the tangent vector. And actually, just for the sake of what I'm going to do next, let me just put a little 0 down at the bottom here. Because called the tangent vector function for r of t. The reason why I'm putting that little 0 down there is because I'm usually not going to be terribly interested in this tangent vector function, but I'm going to be more interested in the unit tangent vector function. So the unit tangent vector function is where I don't just want any old vector that's jumping away from the curve at that point, tangent to the curve. I want one which is tangent and is of unit length, right? Length 1. So the way I do that is I just divide, right, by the norms. So if I don't write the 0, then I mean here x prime of t divided by the norm of x prime of t, comma y prime of t divided by the norm of y prime of t. And you should remember, when we divide by the norm, we do that because it turns things into a... I wrote here, correspond r. You're dividing by the norm of the entire vector, because this will make it unit, right? You're dividing by the norm, so the norm goes to 1. So this is the unit tangent vector function for r of t. Okay, so we'll need this. The other thing we'll need is the normal vector function, really the unit normal one. So I think I called it n of t, and since, did I change my notation? That's fine. Okay, so when you're drawing, let's draw a picture here quickly. If you have a curve and you pick a point, say the curve is going that direction, okay, you draw this nice tangent to it. You can also draw a line now which is perpendicular to the tangent. So this is the tangent vector. And this one, anybody know what this is called? I'll give you a hint. The n up there is the start of the word. What's that? Normal. That's actually right. So this is the normal vector. So when you go perpendicular to the tangent vector, this is usually called the normal vector. Okay. Now, how do you get the slope of something which is orthogonal to a line that you already know?
You inverse it.
You invert it
And turn it negative.
and make it negative, right? So if the slope is m, the slope of the perpendicular is -1 over m. So the way that's going to get reflected in writing down the normal vector is you switch the components of the derivative, and then we're going to negate one of them. I guess I chose to negate this one. That's actually a choice. Okay, so I'm swapping the x and y coordinates, right? This is amounting to inverting things, and then I get a negative on one of them. So this you can call the normal vector function. Oops. I made a vection, a combined vectoring function. And then, of course, what we'll be interested in is the unit normal vector function. Yeah?
The T naught is the tangent vector function,
Yeah.
and the unit tangent vector function is the T.
Yeah.
So it's on top of it. Okay.
Yeah.
So n of t, you just divide by the norm to make it a unit one, a unit vector. So this is the unit normal vector function. For our So let's look at what happens if you take a vector field and you take the dot product of the vector field with its normal vector field. And not with the vector field for F, the normal of C. And we integrate with respect to S, okay, the arc length. So if we do this, then there's a formula that tells us how to do this. Okay. So here we're going back to our R of t, which say goes from a to b. So we integrate from a to b. We have to evaluate the vector field at R of t. And we have to take the... Oh, I didn't do that. Sorry, I did something else at this point. Okay. I take the dot product with n, and then I multiply by... Remember when you first wrote down this ds, this line integral ds, we wrote down the square root, and then you had to square the derivatives? But then we said, okay, that's actually just the norm of the component of the derivative of R of t. So this is times the norm of the derivative of R of t, and then you can do dt. Okay. Good. Now, let's see, do we write this around here somewhere? Here we go. Okay. What happens if I take the dot product of f and n? Right, remembering f is p and q, and n is given by this. Well, let's see. You take the components and multiply them and add them up. So the first component of f is p. The first component of n is this y prime of t divided by r prime of t. So I get p y prime of t divided by the norm of r prime of t. Plus, now I do the second component, which is q times, well, it actually becomes a minus, q times x prime of t divided by the norm of the derivative of r of t times the norm of r prime of t dt. And this is quite nice because those denominators are going to go away. So we get p y prime of t minus q x prime of t dt. Okay, now let's break this up into two different integrals in our head. You have p y prime of t dt. A second, y prime of t dt. That's dy. Right? Y prime of t dt is dy. So this is actually equal to p dy minus q times, we'll see, x prime of t dt. That's just dx. So minus q dx. Now let me rewrite this. This is minus q dx plus p dy. Let me put a little parentheses around that minus q. This is exactly, well, here. I think at this point I can put it back over C. Oh, I should have. When we went from here to here, when we switched from y prime t dt to dy, we should also switch back to C. Right? Because there's no dt anymore. Same thing here. It should be over C. Okay. This is exactly what occurs on one side of Green's theorem, only, well, I have a minus q and a p, but it doesn't matter, right? It should work for any functions in there. So by Green's theorem, I can write this as the integral, double integral over d of, well, it's supposed to be qx minus py. Well, there's a new q in town. The new q is p. Yeah, just like Thursday's the new Friday. Yeah, p's the new q. Okay, so you do py, and then you have to do minus qx. Well, the q, I'm sorry. Yeah, that's right. I'm sorry. Minus px, py. Let's write it down. Qx minus py. We got to mind our p's and q's. This is the problem. Okay, so p was the new q, minus q is the new p. So we get minus q becomes plus qx. Okay. Something funky duty here. Something's not right. We got this backwards. Oh, right. Of course. Okay. It should be px, right? Because it's supposed to be qx minus py. So this is px plus qy. Okay. So this says you're doing the partial derivative of p, and then the partial with respect to x, and the partial derivative of q with respect to y. This is the same thing as if you took the gradient, which is partial of x comma partial of y, and did the dot product with p comma q. Right? Because the dot product here is going to be partial of p with respect to x plus partial of q with respect to y, which is what you get up here. Of course, this component version of it, this is just f. So this is the dot product with f. Of course, this is the div. So let's collect these two formulas. So our first formula, okay, I will omit all of our normal hypotheses, but they're the same as before. The first one is that the line integral of f over c is, did we erase it? Yeah, yes, we did. We put down the double integral of d of the curl of f dot product with k. And the second one is that if you look in the normal direction of the vector field, right, so the normal to the vector field, and you integrate that with respect to s, this is the double integral of the div, the divergence of s. So this curl and this div, which we defined because they were there, basically. I mean, it seemed pretty reasonable to try. Remember, we used them because we used curl originally because we wanted to know when a vector field was conservative. By the way, conservative starts with a C, just like curl. And then we said, well, geez, as long as you have the gradient cross product with a vector field, you might as well write down the gradient dot product with the vector field. We call that the divergence. Right? So it seemed at the time that it was, more or less just obvious to define it, but not that it would be useful for anything. But in the end, it turns out it gives you two very nice ways of rewriting line integrals in terms of double integrals. Okay. How's that clock vis-a-vis actual time? No, still 10 minutes. Is that how you guys have?
Mm-hmm.
All right, so let's pause here and ask any questions. So, sort of the last thing that we're headed for here, well, there's two theorems that we want to get to. One is called Stokes' theorem, one is called the divergence theorem. And to get to them, we need to complicate matters just a little bit more. But it's only going to be more complicated in the sense that there's more dimensions that we're talking about. But in terms of philosophy, we're going to be doing the exact same thing. And we're just going to see that, oh, it just keeps, everything keeps working. So we just finished our section on line integrals, so it only makes sense that we should now do surface integrals. So this is where instead of integrating just over some curve, we're going to integrate over a surface. Now we already saw that if you wanted to integrate over something flat, even if it was some weird thing, you could do that, right? We had double integration. That's what that did. Now we want to do it where it's not just flat, but it might be some weird two-dimensional surface, right? Like the pillow cover or something. You know what pillow cover is, right? Curves. What are you looking at me like I'm just completely insane over here? Who has a pillow cover?
You mean like a pillowcase, right?
Yeah.
Okay. There's difference between pillow cover and pillowcase.
What's the difference between a pillow cover and a pillowcase?
A pillow color goes between the pillow and the case.
What?
I swear to you. I just learned it this weekend.
I would do some
See?
like double protection.
Yeah, it's true.
Let me tell you something. Double protection is important. I am walking proof of that. Well, my kids are anyway.
Or walking failure of double. Maybe? Right?
Something like the weird houses or
Okay, so this is some surface. Kind of weird looking. And I have I can have a function of three variables, say, a scalar function, and I want to know what it means to integrate the scalar function over that surface. So, to do that, we play a similar game as we did to define the line integral. Well, that's a little extreme, don't you think? Okay, I can take this surface and I can project it down onto the xy plane. So when I do it, I get something. I don't know if I use a rectangle. I guess I used a rectangle. Okay. We're going to assume off the bat that this is actually coming of kind of a rectangular shape. That it's rectangular, but it's wavy. Okay. So this is, as you know, this is just to make things easier. Okay. So I have some bad rectangle. So what am I going to do? I'm going to chop it up. And then I'm going to use this chopping to chop up the surface. Okay, so So I use the chopping of the rectangle to chop up the surface, right? Just by shooting these things back up onto the surface and seeing where they go. Okay. And then I choose points within here, within each of these little squares. I evaluate the function at that point, and then I multiply by the surface area of this little square.
Wait, can you repeat that?
Okay. So what am I going to do? I pick a point in here. I evaluate a function. So I have some function lying around, which is, well, let's see, if I call this surface S, then say f is defined on S. So I evaluate f at this point on S. So maybe if I call this Pij, say we've numbered these, i's this way and j's this way. So I call that point Pij. I evaluate the function at Pij. And then if, let's say the whole square itself is called Sij, and that the area of Sij is going to be called, so let's say the area of Sij is always delta Sij. I'm going to take the value of the function at that point and multiply by the surface area of that little rectangular thing. And then I'm going to add this up over all I and j. Say 1 to m and n. And that will give me my equivalent of a Riemann sum. Right? This is, remember, we always did this when we were defining integrals. You choose a point, you evaluate the function at the point, and then multiply by the area or the length or whatever. And then you take the limit as m and n go to infinity. So what is this doing? It's saying, well, okay, at each point I evaluate the function, and that gives me some value. And then I multiply, I'm assuming that it's the same value everywhere on here. I multiply it by the area of that thing. And that gives me some value. And then I add those all up, I take the limit as these things shrink to 0. Okay, so what have we got? Well, we've got ourselves an integral. We define the surface integral, so the integral over S of f of x, y, z. And then maybe I shouldn't use S for both, even though I think I did on my notes. Yeah, I did. Oh well, it's not so bad. Right? The ds is coming, of course, from here. It's both coming from the area of this. This surface integral is the limit as m and n go to infinity. The sum as, say, I and j go from 1 to m and n respectively. F of Pij, where you've chosen Pij's for all these little rectangles, times delta Sij. Okay, so this is called the surface integral of f over a surface S. You should compare this definition to the line integral and to every other integral we've defined. The definition looks almost identical. Oh, okay. I think we should probably stop. So tomorrow we'll pick up by explaining how you compute the surface integral. Talk about it for vector fields. We'll have to talk about the Mobius strip. And then I'll give you Stokes' theorem, and hopefully we'll get to the divergence theorem, or also known as Gauss's theorem.
Is that our last lecture?
Tomorrow, I'll use Tuesday if I have to finish this, but I'm hoping we can get through the rest of it tomorrow. So we're going to finish by basically trying to show that if you, I should say, I wrote one integral here. When you do a surface integral, you use two integral signs. Sorry. yeah, we'll try to show that when you, that basically there's an analog of Green's theorem. Green's theorem said that you could take a line integral and write it as a double integral. And what we're going to do is take a surface integral and write it as a, what do you think? Not as a line integral. That's not a bad guess. No, we're going to write it as a triple integral. That extra dimension pops up.